Okay, so welcome everybody to our colloquium for this week. So today we're very happy to have Carlos Arguelles from Harvard University. So he's a neutrino physicist. He comes from Peru originally. He did his PhD at the University of Wisconsin-Madison, and then he did a postdoc at MIT working with Janet Conrad, and now he's just starting as a new assistant professor at Harvard University. He's won various awards and fellowships through the years, so he was a Fermilab Theory Group Latin American Scholar. He was a finalist for the American Physical Society Thesis Award, and he's won various internal collaboration awards for the IceCube collaboration. So we're very excited to have him and hear about neutrino physics. So just remember that if you'd like to ask questions, you can raise your hand and I'll unmute you to ask, or you can type them in the chat and the hosts will see them and be able to ask. So without further ado, please take it away, Carlos.
Thank you. Thank you very much for the invitation. I'm very happy to give this talk today, and I hope you find it interesting. So today I want to talk about high-energy neutrinos and how can we use high-energy neutrinos to look for physics beyond the standard model. And this relates to two questions that I often talk about in my research and find interesting, which are, how does the universe look in neutrinos? And the other question is, once you see how the universe looks in neutrinos, and in particular, how does it look in high energy neutrinos? Does it look as expected, and the neutrinos doing what they should do? And this is a question that we need to answer through multi-messenger observations. Here in these sort of like glass windows, we have like the three different windows in which we can see the universe right now. So you can see it in optical, which is of course very ancient way of looking at the universe, also in X-rays and gamma rays, and then you can see the Fermi gamma ray satellite. We can more recently see it with gravitational waves. And then we can also see the universe in high energy neutrinos. So by observing the universe in these different ways, we can learn about the universe, but we can also learn about the cosmic messengers that bring information from the places origins to us. And in this talk, I would like to talk about what can we learn about this high energy neutrinos. And this work is connected to this image. This image here is a picture of the sun taken in neutrinos done by the Super Kamiokande experiment in the late 90s. And I want to echo this because when we saw the sun in neutrinos, or first detected neutrinos from the sun back in the 60s and 70s, we did not see what we expected. And this is something known as the neutrino problem, which I will touch later on exactly what it was. But I hope that we encounter a similarly confusing situation where when we looked at the universe in high energy neutrinos or neutrinos at high energies, we find something that doesn't quite match what we expect. So why do I keep saying that I expect things to go wrong and for us to see something that is unexpected? So first I should admit that our theory of particle physics, the standard model, is an incredibly successful theory. It's built upon this gauge structure. This is SU3, SU2, U1 symmetry, has these 18 parameters, and it has an amazing agreement in observable after observable. But you could argue that for a fundamental theory, this is quite a complicated theory. So here I have outlined the standard model particle content. So you can see the quarks, the leptons, and the antiparticles, as well as the bosons in the lower row. And you can see that the standard model is organized in these rows and columns with these particular patterns. There is something known as a flavor structure, which is currently not explained in a fundamental way. So it has this odd structure. So for a fundamental theory, this to me looks like complicated. And I think it's a good time to appreciate that last year was the 100-year anniversary of the periodic table. And the periodic table somehow is analogous to this problem. In that case, we grouped elements by their common features. in this arrangement. And of course, this arrangement had an underlying reason, and that reason is now quantum mechanics and so forth. I think similarly, the standard model structure probably has an underlying theory that simplifies it. We also know that the standard model is incomplete because it does not seem to describe all we see in the universe. We know that today, the standard model which describes the atom only represents about 5% of the universe energy content, and the rest is yet to be find out what it is. And finally, I want to point out that, and this is the reason personally I work with neutrinos, is that in the, let's say, standard way of writing a standard model, neutrinos were supposed to be massless, and they actually have a mass, and I'll tell you why do we know they have a mass in some slides from now. And so how do these particles get a mass, why they're massive is an ongoing question. And in general, the fact that neutrinos did something unexpected, I think makes it interesting probe to see if they will do something else. Okay, so with that motivation, this is my plan for this talk. So first, I'm going to tell you about neutrinos and the IceCube Neutrino Observatory. And then I'm going to tell you about 3 different ways in which you can use high energy neutrinos, in particular IceCube neutrinos, to look for new physics that are motivated by the things I was talking to you earlier. So let's talk about neutrinos and IceCube. So there are 3 light neutrinos. They're very light neutrinos. They're much lighter than the electron as far as we know it. So where do these neutrinos come from? Neutrinos are produced in a variety of sources. There are natural sources and anthropogenic sources. So we have neutrinos from the sun, and that's the picture I showed you in the beginning of this talk. There are neutrinos producing cosmic ray showers. Those neutrinos are known as atmospheric neutrinos because they're produced in the atmosphere. And I will talk about atmospheric neutrinos later in this talk, and those will be an important signal for IceCube. There are also neutrinos that come from a supernova. Those are also going to be, for my definition of high energy, they're going to be low energy neutrinos. And you can also have neutrinos from other astrophysical objects, but the supernova ones are say the classic ones. There are also neutrinos that are remnant from the Big Bang, and those are about, in abundance, around 10 to the 9 per cubic meter. Anthropogenic neutrinos, I will not talk about anthropogenic neutrinos, but we can make them using accelerators or reactors. Neutrinos only interact via the weak force, which means that the interactions of them happen very rarely. At the solar neutrino energies, which is a handful of MeVs, the neutrino cross-section with a nucleus is around 10 to the minus 43 centimeters squared. And if you compare that to the cross-section of a proton-proton fixed area experiments, it's typically of the order of 10 to the minus 24 centimeters squared. So there is a 10 to the 20 difference between essentially strong interactions and this weak force. And that means that the neutrino is going to be able to travel through a lot of matter. And for example, you have a solar neutrino at that energy, it can easily go 200 Earths if you pile them all together. Okay, so when neutrinos interact, how do they interact? They're going to have 2 types of interactions. The first one is known as a neutral current exchange. I draw it here. In these Feynman diagrams, you can think time as going in the horizontal axis and the position sort of going in the vertical axis. And here you have a neutrino that exchanges something known as Z boson with a D quark, and it scatters. So this is more like a normal like ball scattering, where the particles that begin are the same particles that end. But the weak force also have a different kind of interaction, and that's known as a charge current interaction. A charge current interaction, the neutrino exchanges a charged particle. In this case, is going to be a W boson. The charged particle is going to make the neutrino change nature. So instead of having a neutrino come in and a neutrino comes out, you're going to have a neutrino comes in and a charged particle comes out. So the different charged particles that can come out of the neutrino interactions allow us to label the neutrinos. And this label that we put the neutrinos, we call it flavor. So we have 3 neutrino flavors. There's the electron flavor, which produces, when having a charged current interaction, an electron. There's the mu neutrino flavor, which produces a muon, and the tau neutrino flavor, which produces a tau. On these flavors, I will tell you, just to start, that the electron neutrino and the mu neutrino are the most studied of the 2 neutrino flavors, Tau neutrino is less steady because the tau has a much larger mass than the muon and the electron. It's much harder to identify, and that will be important later on. So you can organize the neutrinos and the corresponding, we call them partners, in these doublets in the standard model. So we do not see the neutrinos because the neutrinos are neutral particles. What we can see in our detectors are going to be charged particles. And we can see them in multiple ways. We can see a neutrino coming along and it has some interaction. You have a charge current interaction, for example, making an electron, a muon. And then those charged particles will emit light in various different ways. They can ionize material, they can emit scintillation light, and in particular, they can also emit Cherenkov radiation. So Cherenkov radiation will be emitted by a charged particle that's going faster than the speed of light on the medium. And you can see here an image of a Cherenkov detector. This is actually the muon detector. And you can see that Cherenkov ring produced by a muon emitting Cherenkov radiation. Cherenkov radiation will be important for this talk because that will be the main kind of light that we can see in the IceCube neutrino observatory. So we can see different neutrino types by identifying using ionization, scintillation, Cherenkov, what was the outgoing charged lepton. But there's something very strange happening with neutrinos. The neutrinos can change, they can morph within flavors. We call that morphing phenomena neutrino oscillations. And let me tell you how that works. So you start with a known neutrino source, in this which is shown in this box in the square. In this particular example, that neutrino box is a muon neutrino. And then you put some detector at some distance from it, and you try to count how many electron neutrinos or how many muon neutrinos you have. And what you're going to see is that the number of muon neutrinos that you see is going to go down, while the number of electron neutrinos goes up. And then subsequently, it goes back to be muon neutrinos and electron neutrinos. So it does this kind of periodic behavior as a function of length, which is why we call it oscillations. The frequency in length of this periodic behavior happens to be related with the mass square difference between the two neutrino mass states that are involved in this problem. The amplitude of oscillation we usually quantified in terms of something called the mixing angle, which just tells us how much are they mixing. So in some sense, the neutrinos have some kind of internal clock that makes them at some sort of like natural frequency move from being a muon neutrino to an electron neutrino back and forth, back and forth. And this is really important because the fact that the neutrino has this internal clock implies that they must have mass. If a neutrino, if your neutrino were to be massless, it cannot have a sense of time because there's no way to boost it. So this is, now we understand that this phenomena is actually related or can be explained in quantum mechanics via this neutrino Hamiltonian. So here is the neutrino kinetic, say, Hamiltonian. So you have that is the mass square divided by its 2 times its momenta. And we usually write it as it's shown in the right in neutrino physics. So we write it by the neutrino energy because the momenta and the neutrino energy are quite similar, as the neutrino masses are very small. And then what's going to enter in this parenthesis term are the mass square difference, going to be the frequency. And there's this term U, which is going to tell you the mixing. Oh, sorry, yes, I mixing on the left. I'm going to tell you a little about what that U represents, and that basically represents how much of each of the neutrino mass states have a given flavor states. So how do we disentangle this problem? We do 2 types of experiments in neutrino physics. One of them are called appearance experiments. And how those work is you start with a certain flavor of neutrinos. So that's the, let's say, this muon flavor. And then you ask yourself, do I see a new flavor in my detector that's far away? And that can be, let's say, an electron or a tau flavor. And that's very nice because if you have guarantee that your initial beam, for example, is a very, very pure neutrino beam, and you certainly see something that looks like an electron on the other side, you know that an electron appeared, and that's an appearance of we call that from mu to mu e. You can also do these appearance experiments, and in these appearance experiments, you start with a certain flavor. Let's say, again, my mu neutrino, and then you ask yourself, if I start with 100 mu neutrinos and put my detector farther away, do I get the right number of mu neutrinos I expect from just distance scaling? And that these actually, you will realize obviously that these two experiments are correlated. So if I have 20% of disappear, I should have 20% appear somewhere else. And so by doing different measurements at different energies and lengths, we can figure out these oscillation amplitudes and figure out what the neutrinos are made of. And that brings us to what I want to call this standard neutrino picture. This is kind of a little heavy slide, but what matters is what's on the left. And what's on the left is that we know that there are 3 neutrino mass states, which we know as nu1, nu2, and nu3. The nu1, the different colors in each of these mass states are the flavor of the mass states. So the nu1 is mostly electron neutrino, and then it has a smaller part of mu and tau neutrinos about equal proportions. The nu2 has less amount of nu e, and then equal proportions of mu and nu tau, or roughly. And then there is nu3, and the nu3 is the state that has the least amount of electron neutrinos. We know that nu1 and nu2 are separated by something that we call the solar mass difference, and that's given by the number on the right. And then there is a larger mass difference between the nu2 and nu3, approximately 100 times larger. And that mass difference was initially measured with atmospheric neutrinos, so we call it the atmospheric mass splitting. The fact that the nu3 is shown in this diagram is above them, we call the normal way of ordering them, so 1, 2, 3. But we actually do not know if nu3 is heavier or lighter than the nu1 and nu2 mass states. So it could be also like you have nu3, the nu1, and nu2. This is known as the neutrino ordering problem. The composition, so these elements we actually know fairly well. We are know them to 3% level. And then the issue of, there is also a possibility of having a CP violating sign in this problem that we still have not measured. So this, if you take these numbers essentially, and you make neutrino experiments at various distances and lengths, you will be able to predict fairly well where you will see neutrinos appear and disappear. But the path that towards this picture was not very smooth. It was actually very confusing. And I want to remind people of how confusing it was and what lessons we learned that we could use in looking for physical high-energy neutrinos. So first, I want to remind people something about the atmospheric neutrino problem in the 90s. And that was the fact that in the 90s, experiments that look for mu neutrinos, so these are disappearance experiments. So they were trying to count how many mu neutrinos you should have. So here in the horizontal axis, you have different experiments. And in the vertical axis, 1 means I see the number of mu neutrinos I expect. So you see that here there are like 3, maybe 4, if you count Sudan, that see less mu neutrinos than what you should expect. Or there are 2 experiments that do not. So this was a quite confusing situation. So to resolve this situation, you needed an experiment that had just larger or more statistics because servers were too large. And so Super Kamiokande managed to solve this problem. And you can see here the end solution in the right. So you see what the Super Kamiokande error bars on that R quantity were in the end. But I want to point out something of why this problem was particularly hard. And this was hard because the Kamiokande initial result was somewhat offset from the Super Kamiokande result. You can see it on the left. The Kamiokande result is in black, and the right result of Super Kamiokande is quite far away. So to resolve this problem, we needed a larger data, that's more statistics. And if you look at the earlier results between Kamiokande, so you will see these tensions of what is an artifact between is getting accidentally the wrong numbers. Another problem, and this is what I was hinting in the beginning of this talk, was the solar neutrino problem. And the solar neutrino problem is interesting as well. So here in these plots are a little complicated to read, but what you have to notice here is that the data in these plots, this is what made by John Bacall, the data in this plot is shown as blue bars, and the theory is shown in yellow. So the blue bars that are next to it, like sort of like a rocket, those are experimental measurements. And what you can see here is that the theory lines are just too high with respect to experimental measurements. And what that means is that you see too few electron neutrinos from the sun compared to what you expected. And this was a very long-lasting problem. And the reason of how we were able to solve this problem is to look at this problem in a totally different way. So we need an experiment that had a different experimental capability. And that experiment turns out to be the snow detector. And so in snow, we can measure not only the electron neutrino fraction, which is on the left here, but also the all neutrino flavors, which is on the right. And so you can see here that when you count all of the neutrino flavors, you actually make it match. But when you look only at the electron neutrinos, you see that they are less. But if you say, well, that just means that it's because the distance between the sun and the Earth, and try to figure out what's the right oscillation parameters, you actually will get the wrong answer. There's another component to solve the solar neutrino problem. And the second component is that in the sun actually has a very large density of electrons, and that modifies your standard neutrino Hamiltonian, which I was talking to you about earlier, with this additional potential. So this additional potential allows the modifies the oscillation probability. So to solve the solar neutrino problem, we need an experiment that have a different experimental capability and also some theoretical understanding of what's just new. So these lessons I want to take away here is that the new physics we're going to stumble upon are also going to usually appear in a very confusing situations. And in neutrino physics so far, in the new physics has appeared as some modification of the vacuum Hamiltonian, which makes us look toward oscillations. So what other ways could we think about modifying neutrino oscillations? So what can I add to this? So if I add new particles, I'm always going to introduce new oscillation frequencies. If I add new forces, so new interactions between neutrinos and matters, those are also going to modify how the oscillations happen, how the frequency change. And of course, if I mess up space-time, so I may mess up the way new states evolve, I'm also going to introduce new oscillation frequencies. So in this talk, I'm going to try to explain you how we can use hidden neutrinos to look for these sort of things. So we'll be looking at effects that are related to flavor morphing. We're going to look for things that change flavors in unusual ways. And if you see that, you maybe see something interesting in physics. And for that, let me tell you, how do we see different flavors within IceCube, and what is the IceCube Neutrino Observatory? So the IceCube Neutrino Observatory is in the South Pole, so you're probably somewhere around Ohio area. This image is at the scale. So here the Antarctic continent and the US are at the same scale. You can see Antarctica is quite a large place. If you were to go there, this is one of our students very close to the South Pole marker. That's how it looks. And the IceCube Neutrino Observatory is actually buried in this glacier that makes the South Pole. It's buried approximately 1.5 kilometers below the Antarctic glacier, and it's comprised it instruments approximately 1 cubic kilometer of very clear Antarctic ice. That corresponds to about 1 gigaton of ice. And it's making this sort of like array. The array is comprised by these digital optical modules, which are PMTs, which are encapsulated by these pressure-resisting vessels that have their own data acquisition system. And so this grid is approximately regular and allow us to monitor this big chunk of ice. So one thing we can do with this is we can look for charge current mu-neutrino interactions. And that's, for example, you have a mu-neutrino that's going to the planet. It can interact in the ice below the detector. And when it does so, it makes a muon. That muon is going to make Cherenkov light. And the Cherenkov light emits in a very particular geometry. And we can look at the time of arrival of that light and figure out the muon direction. We can also figure out the neutrino event energy. So here is the IceCube. It's one of our event displays. It's a simulation. So here you see these little spheres. If the sphere is big, it means that lots of charge have been deposited in it. If it's small, it means less charge have been deposited in it. And then the color of the spheres is going to tell you the time. So red means earlier times and blue means later times. So this is a muon that went its way from the left part of the detector to the right part of the detector. And then if we sit around the trajectory of this muon, we can actually figure out the energy loss. And it so happens that at these very high energies, the muon d dx is proportional to the muon momenta. So when measuring the energy losses, we actually can measure the energy. These events are really big. Here I put it in comparison approximately to the Rock Hall of Fame in Cleveland. And so these are really 1 kilometer length objects and quite massive. So that's how we see mu-neutrinos, but we can also see all of the neutrino flavors. Mu-neutrinos, the ones on the left here, we can see when they're actually starting the detector or when the mu just goes through the detector. Electron neutrinos, we can see when the electron starts in the detector or when it's maybe close to it. Tau neutrinos, we can identify when it happens inside of the detector. And I will show you today how we were able to find our first tau neutrino events. And like I was saying, this is very particularly important because tau neutrinos are hard to see in general. These Feynman diagrams translate to us to event topologies within a detector. So in the left one, we have charge-current mu neutrinos. They make this long trajectories across the detector. On those, the end resolution is a factor of 2, and angular resolution is better than 1 degree. Neutral current events and charge-current electron neutrino event make these blobs. On that, we can measure the energy with around 15%, and angular resolution approximately 10 degrees. And then we have tau neutrinos. So tau neutrinos are special because when you have a tau, it can interact in the location of that red blob approximately. And then this tau is going to be very, very boosted. These are very high energy events. So the tau is able to live some distance before it decays. To give a sense of scale, if I have a 1 PeV tau, it will go approximately 50 meters in the ice before it decays. And we can see its double cascade signature at 100 TeVs. Tau neutrinos is something that's special for IceCube, and it's very difficult to do in most neutrino experiments. And the reason is twofold. First of all, the charge tau neutrino to mu neutrino cross section is much smaller. So here you see the ratio of those cross sections is the vertical axis function of the neutrino energy. Most neutrino experiments operate below 20 GeV, so the cross section is suppressed by a factor of 10 or so. Second is, once you manage to produce a tau neutrino, you need to identify it as a tau neutrino, and that's hard because you need to identify the position when the tau neutrino is produced and then when it decays. So the distance, the decay length at 10 GeVs is approximately 0.5 millimeter, and the decay length at 100 GeVs is 5 millimeters. So it's really difficult, and that's one of the reasons we have seen very few tau neutrinos. Luckily in IceCube, we have very high energy events, and this shows you the energy distribution of IceCube muons in the horizontal axis. And you can see that this goes from hundreds of GeVs, TeVs, all the way up to 100 TeVs. So we have very, very high energy events compared to accelerator beams, which allow us to identify these events. Now, where are these events coming from? Most of these events come from cosmic ray air showers. Like I was saying earlier, if you have a cosmic ray that hits the Earth's upper atmosphere, it starts a cascade of particles. The cascade of particles will produce pions, kaons, and other things. Those pions will decay, making neutrinos. Atmospheric neutrinos are produced by these cosmic rays. Cosmic ray incidence on the planet is approximately isotropic to 50% level. And that means that you are going to get cosmic ray from all the directions. And this allows me to define something known as the zenith angle. The zenith angle is the direction with respect to the south pole. So zenith angle of 0 just means I look through the south pole, and a zenith angle of pi goes through the whole planet. IceCube is going to see a lot of atmospheric neutrinos, around 30,000 of those per year. And they are going to dominate all of the energy range below 100 TeVs. Atmospheric neutrinos, actually the flux of atmospheric neutrinos goes down with energy and is maximal closer to the pion rest mass. But you can see that our atmospheric neutrino spectrum does not look like that. It looks like this sort of triangle shape where the flux is going up. The reason is that this sweet spot of a TeV comes from the flux of atmospheric neutrinos going up as you go down in energy, with the detector efficiency going up as you increase in energy. So the lower part of the atmospheric neutrino flux is being cut off with the fact that our detector is very sparse. The typical distance between our strings is like 100 meters. So the sweet spot of our atmospheric neutrino events, when most of them happen by a combination of our geometry and the flux of neutrinos, is close to a TeV. At higher energies, above 100 TeVs, we see astrophysical neutrinos. Astrophysical neutrinos, you can sort of see them from this plot, that you have this falling spectra of atmospheric neutrinos as black dots, and then you see that at the end, this sort of harder tail appears. Those are astrophysical neutrinos. So where are they produced? Astrophysical neutrinos are produced, well, we don't know exactly how they're produced, to be honest. It's a matter of active investigation. But the idea is that there's cosmic accelerators that somehow, yet unclear, accelerate protons to high energies, and these protons interact with ambient radiation or dust around the the acceleration region. In that region, they can again start a cascade of particles, and those particles, for example, can start producing pions in the cascades, and then you again have neutrinos, gamma rays, and cosmic rays. So in this sort of picture, the three of the cosmic messengers, cosmic rays, gamma rays, and neutrinos are related in their production. This is yet to be tested, but we do have some partial evidence of this. 2 years ago, we announced the observation of a high neutrino event that had 300 TeV of energy in coincidence with a laser that was flaring in gamma rays. And that neutrino went across approximately 4 billion years old. Was approximately 4 billion years old. And this is so far the only known candidate high neutrino source. But this is not the only high neutrino we have seen. We have seen more of them. This is one of our latest plots of high neutrino content. Here in the horizontal axis, you can see the energy that the neutrino deposits in the detector, and the vertical axis is the rate. Above 60 TeV, which is the region which is not shaded, there are approximately 60 high energy neutrino events here, of which there are 40 of these events that have 1 PeV of energy. And one thing that's interesting about this particular high neutrino data set is a tau neutrino. So the first tau neutrino set was found in this observation. Its energy was approximately 90 TeVs. And how we identify the tau is, again, we look for the first band when the tau is produced, and then a second band when the tau decays. And so you can see the event display here. There is very difficult to see a separation, but you see these little squares around the display. And that is, what you see here is the charge deposited in the PMTs around the interaction vertex as a function of time. So you can see that, for example, in the rightmost panel, there's a first peak of charge that's seen, and then a second peak of charge, and the same is true for nearby cases. So we think this is evidence for this double bank structure. So we're interested in anomalies related to neutrino flavors, and neutrino flavor changing has been how we made progress in the past. So we want to pursue anything that looks strange neutrino flavor changing phenomena. The IceCube Neutrino Observatory is going to see neutrinos at very high energies, and central mass energies of higher neutrinos are similar to LHC energy, which is going to allow us to look for very unusual interactions, and we can have a spatial proof in tau neutrinos. And the two types of neutrinos we see are atmospheric neutrinos and also astrophysical neutrinos. And now with that sort of capability in mind, now I want to give you my 3 examples very fast. So my first example is about sterile neutrinos. So neutrinos have something that's funny, and that they are left-handed. So you could ask yourself, what is the right-handed neutrino? And another one that could be related, which is some experimental anomalous observations that I will tell you a bit in a minute. So 2 experiments were made in the last decades that look for appearance of electron neutrinos in muon neutrino beams, and those are the LSND and muon experiments. So in the LSND experiment, you had a pion decay at rest source that produced a very pure muon antineutrino beam, and what they look for is electron antineutrinos appearing in their detector. And you can see the top plot here is the number of electron antineutrinos they see on top of their background, and you see that they see more than what they should see. And like I was saying, and similarly for the muon experiment, but in different configuration. So these are appearance experiments, so too many electron neutrinos essentially. And like I was saying, this can be understood like an oscillation behavior. And if you take the energies and lengths relevant to this problem, you figure out that the mass square relevant for this problem is around 1 electron volt square. So this is often explained by introducing something known as a sterile neutrino. So what's a sterile neutrino? A sterile neutrino is does not interact via standard model forces, so does not participate in the weak interaction. And we usually think that it's heavier mass states, and it has components of it which is part of the active flavors. So the game here is to figure out what is the mass of the 4 neutrino state, if it exists, and how much of the 4 neutrino states is electron, muon, and tau flavor, which are the colors on the top bar. So the electron, muon, and tau flavor, the amount of muon, electron, and tau flavors in the more heavy mass states are going to control the neutrino amplitudes. So the mu neutrino to electron neutrino to electron neutrino, and mu neutrino to mu neutrino depend on these three parameters. And as you can see, that depends on these equations. And so what we want to see is if we think that LSND and minimum saw an appearance of electron neutrinos, that means that they saw mu neutrino becoming electron neutrino. That means that the product of UE4 times U mu4 cannot be zero. And that means that both the red blob and the blue blob in this slide cannot be zero. So what we've been trying to do is look for evidences of disappearance of electron neutrinos and mu neutrinos at similar frequencies. So you can take all of the data in the planet and you can combine them all together and you can figure out, is there evidence for such a neutrino? And the answer is yes, but there's going to be a big but in a second. And the solution is those parameters there, not particularly important, and it's extremely significant. The problem is it doesn't work. And the reason it doesn't work is the following. If you take the neutrino data and you split it into sets that look for mu to electron neutrino versus sets that look for the neutrino remains the same, you get these two regions. So for appearance experiments, you get large mixins, which is the horizontal axis, and small masses, which is the vertical axis. Whereas for disappearance experiments, you want small mixing, horizontal axis, and large masses. So this just doesn't make any sense. So the experiment is in total contradiction. And this is sort of like, that's why I wanted to evocate earlier this like confusing situation in the 90s of atmospheric neutrinos. Like sometimes you see something and it's not there. This is sort of to even worse, the much worse degree happening here. So it's extremely confusing. So IceCube has looked into this and tried to think about this in a novel way. And what we do in our case is we look for mu neutrino disappearance. So in IceCube, mu neutrinos are going to traverse a large amount of matter. And in that case, Hamiltonian is not going to be the one I showed you earlier, but it's going to be this one in the bottom that has this matter effects. And what that's going to do is you're going to have that the neutrinos are going to convert a lot of them from mu neutrinos to sterile neutrinos. So you can see this in this plot here. This is a trajectory of one neutrino going vertically through the planet, and it's becoming essentially in the anti-neutrino case 100% sterile neutrino. This is sort of analogous to the conversion that happens in the sun, if you're interested. So if you look at where that disappearance happen, well, the disappearance should happen somewhere at TeV, and that's very good for us because that's where it has lots of neutrinos. So how do you look for this? We essentially look for this by looking at the direction, which in this plot is the horizontal axis, which is the cosine of that angle in the planet, and the energy, which is in this vertical axis. And what you're looking for is that dip there that's in red, somewhere around the TeV. That's where the neutrinos are converting to sterile neutrinos. So these plots are for a fixed mass core difference, somewhere around 0.1. And then what I do is I increase the amount of mixing between sterile and active. And what you see is that these disappearances move from left to right. Now, if I fix the mixing, but I move the mass from large to left, as I go from left to right, what it does, it moves it in the energy location. So by looking at different energies and directions of my muons, if I see somewhere in particular energy in direction that I see less neutrinos, I have found it. So we have done this new search, which is called MEOWS, Matter Enhanced Oscillation with Steriles. And this is uses 300,000 mu neutrino events, these charge current mu neutrino events. And I want to show you this plot because I think it's really neat. We know that atmospheric muons have something known as seasonal variation because the Earth's atmosphere temperature changes. And so correlatedly, neutrinos produced in the atmosphere should also change in rate. So what you see here is the seasonal variations of atmospheric neutrinos in the atmosphere through the last 8 years, which is just, I think, quite stunning. So we blended 300,000 events, and we look for disappearance of mu neutrinos, and the answer is we didn't find anything significant, so our limit is shown in blue, and we have a slight hint at 90%, but nothing to worry about. So the takeaway from sterile neutrinos is that the situation is very confusing, but IceCube can look for sterile neutrinos in totally new ways because we have large matter effects. We have mostly seen agreement with disappearance, but our best fit solution is in some slight agreement with global fit solutions. Now I want to quickly give you another examples of what we can do. So most experiments, we can look for dark matter annihilating the small particles. In particular, you can look at making gamma rays and making neutrinos and other things. So for example, you can look at dark matter, very heavy dark matter, like PV scale dark matter, annihilating into a pair of neutrinos. And what that does is if I look at around the galactic center, where it should accumulate, I should see an excess of events. So we didn't see any excess of events. And so what we do is we put a constraint on the annihilation rate of dark matter into neutrinos. And this you can do with all the neutrino telescopes. And in particular, you can do this with all of the neutrino experiments. So here I show you all of the neutrino experiments that we could think about. And the horizontal axis is the mass of the dark matter, and the vertical axis is the cross-section multiplied by the velocity. So of the dark matter making to a pair of neutrinos. And so you can see that essentially this is a constraint that tell you like you cannot exceed this kind of annihilation rate, but how many neutrinos we're gonna see. And IceCube, what it does, it dominates the higher energy, the higher mass region. So these limits require precise prediction of the dark matter fluxes. And for that, we have this new package called Caron. I want to just advertise here that we put on the web that allows us to do latest calculations of like dark matter production to neutrinos in the Earth and galactic halo. That we can do with all the experiments, but there is something that only IceCube can do, and that is the following. So we have seen astrophysical neutrinos, and those are the ones I showed you earlier. And astrophysical neutrinos are coming from very far away. They're coming, as far as we know, for all directions. So what you can do is you can look at the neutrino sky, and if dark matter and neutrinos have some kind of secret interaction, they talk to each other in some way. If a neutrino shown here in green goes to the galactic center, it will hit a large dark matter density. Whereas if it goes orthogonal to the galaxy, you will see less of a dark matter density. And that means that a dark matter neutrino interaction introduces an anisotropy in the neutrino sky. So here is the neutrino sky. These are those events I show you. These are astrophysical neutrino events, crosses and excess. It looks like the center of this plot, by the way, is the galactic center. And the color scale is how much dark matter there is. It looks by eye like the galactic center has no neutrinos there. But I swear to you that if you statistically analyze this, you get that this is actually a uniform distribution. But if this were to be true, this will be like even more and more empty. So far we have found no signal, so we put constraints. And so basically what you do is you establish a couple of models of how the neutrinos and the dark matter can interact. Here are two examples. And what you can compute is how many neutrinos you should see less in the galactic center. And depending on your interaction type, here are two examples, they will do different things in the energy distributions. These constraints on dark matter neutrino interactions are actually quite competitive with cosmological constraints, where you have potential lots of neutrino dark matter interactions. So the model on the left, we have like a vector mediator with a fermionic dark matter neutrino interaction. And the horizontal axis on the left plot is the dark matter mass, and the vertical axis is the mediator mass. The color scale represents the log of the maximum allowed coupling of this process. And so what I have sort of divided here with this purple line is the region where the IceCube results are the most constrained results, and the bottom line where the cosmology does better. And here by cosmology, I mean things like large scale structure. So dark matter neutrino interactions in IceCube are unique because you can look at astrophysical neutrinos. We can also look at very high energy dark matter if it decays to us. And these limits are just going to get better as we get more data. Now let me talk about a final topic of this presentation, which is looking for new symmetries. Like I was saying in the beginning, neutrino oscillations are essentially the neutrinos have this internal clock whose frequency is given by the mass square difference between neutrinos. You can model that like this Hamiltonian evolution. So if you introduce something like Lorentz Violation, what you're essentially doing is you're modifying how time changes. And what that can do is introduce new flavor conversions in your new oscillation frequencies in your neutrino patterns. So I'm going to look for astrophysical neutrinos and look if they may change in flavor. So astrophysical neutrino sources are unknown, but we typically arrange them in 3 types of sources. They're going to be pion-dominated sources, and those are produced by pions. Pion decays into muon plus mu, muon decays, and then you have electron plus a pair of neutrinos. So these sources produce in flavor ratios, 1 UE per 2 nu mu's and no nu tau. So we call it a 1-to-0 source. Now you also have muon damp sources. When a muon damp sources, the pion is produced in an environment that has a large magnetic field, and the large magnetic field, the muon loses energy very fast, so it does no longer yield higher energy neutrinos when it decays, so you only get 0-1-0 at highest energy. You can also have neutron production in the sources, and of course neutrons can decay, and then you have nu's only, so it's levels at a 1-0-0 source. In a real scenario, it's a combination of these things. Most sources that are proposed in the literature are pion sources. So we organize the neutrino flavor in this sort of something known as flavor triangle. So each axis in the flavor triangle tells you the fraction of flavor. So the horizontal axis is the electron fraction at Earth, the right axis is the muon fraction at Earth, and the left axis is the tau fraction at Earth. Notice that the numbers in this axis are slanted in a particular direction. That's important how you want to read this plot. I'm going to tell you how this plot is read because it can be a little confusing. So if you have a point here, it means you have 100% muon neutrinos and 0% of the rest. If you have a point here, it means you have 100% electron neutrinos and nothing of the rest. If you have a point here, it means you have 100% tau neutrino and nothing else. And if you're in the middle, you go along the directions of the numbers to read it. So this, for example, has 30% or 33% of each of them. Okay? So we know these 3 categories, so we can use neutron oscillations to predict where things end up at the triangle. So we did this with these colleagues and look at those all references as well. But essentially, for example, if you have a pion source, that's a 1-to-0, all of the sources are assumed to be pion sources, then you end up inside of the yellow region after you include oscillations. So very, very close to equal flavors. If you have muon damp or a tau source somehow, that's also very close to 1-to-1 to 1. The neutron sources are the ones as farthest away, and in those cases, you're going to get larger contributions of electron neutrinos on Earth than in the other cases. If you have a combination of these different sources, you tend to end up essentially in a linear superposition between these ranges, but that means yes, around the center. So what is important about here is that if we manage to measure the flavor composition of astrophysical neutrinos and we end up outside the color regions, then we have found something really interesting. Of course, the problem is we don't have many astrophysical neutrinos. We only have like 60 or so. And so what we do is we arrange them in these 3 morphological categories, so tracks, cascades, and cascades, to identify roughly 2 muon neutrinos, all flavors, and tau neutrinos. And so these are one of our latest measurements, and you can see most of the triangles still allowed here. The result is shown in black, and the equal flavor, which is inside the 1 sigma region. So what can happen to flavor triangle if I include Lorentz Violation? So what the idea here is that there may be a Lorentz violating field that permeates the universe, or for example, it doesn't need to be a Lorentz violating field, but for example, it could be a interaction, a flavored interaction between neutrinos and their matter. That will also work. By some secret interaction somewhere, the neutrinos from the source and us. So we are agnostic of how Lorentz violation is broken, if it's broken. So what we do is we have our Hamiltonian, which has a standard piece, and then we have these new physics operators. So what we do is we write all possible operators that can modify the neutrino propagation. So we organize the operators by the dimension of the operator in the Lagrangian, and then U here is essentially the flavor structure of that interaction. And lambda is the scale at which the operator is suppressed. And so what they do is they can modify these flavor trajectories. If you go one example here in this flavor triangle, so you have these neutron sources, for example, which is the green one, and then there is this new interaction here, which happens to be a electron tau symmetric or equal in electrons and taus. What that does, it just moves your triangle like that. So you can play this game and put different textures, flavors, interactions, and it will give you different trajectories in this flavor triangle. So unfortunately, the only things you're going to be able to say is that we are not in the corners, which just means that we don't like interactions that preserve initial flavor. And so what it does, it's runs to this plot here. So the horizontal axis is the initial flavor contribution. So 0 here means muon source, then 1/3 is pion source, and right is neutron source. And you can see here what is constraints. Again, this depends on what I assume the flavor of the interaction is. But what's interesting that it really goes all the way up to the Planck scale. But the caveat is we don't have enough information about the source at the moment to really pinpoint this. So IceCube astrophysical neutrinos have some bridge to Planck scale just because of the distance they're getting, which is interesting territory for GATS and so on. So I hope I have convinced you of IceCube and how you can use high neutrinos to do various of things that I hope are interesting. And IceCube has this very broad science program that I show in this octopus plot here. And that program potential keeps growing, which is going to grow in 2 different phases. So the first phase of this is something that we know as the IceCube upgrade. The IceCube upgrade is the inclusion of 7 new high precision strengths inside the IceCube volume. So here you see a top view of the IceCube array. In blue, you see the IceCube strings, and that's the ones I've done use for this talk. In green, there is a subsection within IceCube, which we call deep core, and deep core is more tightly packed than the normal IceCube strings, and we can use it, and we use deep core to make standard oscillation measurements. The new arrays are called the IceCube upgrades, so here in red. Those are even more tightly packed, and they're not only tightly packed in the horizontal direction, but we also will pack them more in the vertical direction, as you can see in the inlet. And that will allow us for improved flavor identification. So we are going to be able to resolve those double bands better if they have been close to a region. This is already funded, and we hope to install it somewhere in 2023. The IceCube, the second of the upgrades is IceCube phase 2, and for that we have a 10 times larger IceCube. So here you can see the current IceCube array in red, deep core in green, and in darker blue the upgrade. The upgrade will start installation in 2023, finish 2025 or 6, and then the IceCube Gen 2 probably will start construction in the later part of the decade. And we expect it to be 10 times larger. So what can we do with that? So if we already have 12 years of IceCube data, or we have 2 years of IceCube data when we have the upgrades, and so when we have phase 1 of the upgrade completed, we hope to shrink that big triangle I showed you to just this green region here. And when we do that, here you can see these markers, this square, circle, and triangle. That tells you the locations of muon damp, pion, and neutron sources. So we will be able to pinpoint which of the source configuration is more relevant. And of course, if there is any additional new physics, we will have some more sensitivity to it. Okay, so I think that neutrino physics we're going through quite interesting times. There are these oscillation pictures, and it's a very confusing situation. The dark matter is, of course, a big problem, and maybe it's related to neutrinos, and IceCube brings new ways to look into those, and also we're able to explore Planck scale regimes. I think the IceCube set is going to keep enlarging, and hope everybody, if you are interested, do not hesitate to contact me. May your physics be BSM, and thank you very much.
Okay, thank you very much. So we'll now open it up for questions. So you can raise your hand, or you can type in the chat. So Pavel, let me
let me give you more time to the students. If they have questions, then I will go at the end.
Okay. So yeah, any students get priority.
Hello.
Hello?
Yeah, my name is Kair, and I mean, I'm not sure whether it would be appropriate to ask this. I actually have a question about the technical things about the IceCube. Can I also ask about that?
Yes, please ask it.
I mean, yeah, you told me that the IceCube already done for the 12 years for the data collecting, and the photomultiplier tubes, they should be buried in the deep inside of the south core. And I mean, I think there would be like hardware problems if they bury such kind of photomultiplier tools more than a decade, then how does the IceCube guys monitor that, or how does they maintain and replace the photomultiplier tool which is not working or which is working bad?
This is a really good question. So just to see if I understood your question is, an IceCube PMT stops working, what do we do? So we cannot do anything because it's buried 2 kilometers below the ice, so we cannot take them out. Luckily, these PMTs so far have been quite stable. We do not have many of them lost per year. Our detector has approximately 6,000 of this PMT, and I think our loss rate so far in 10 years is on the order of 1 or 2%. So I think part of the reason for this is that being in the ice is very stable, temperature-wise and voltage. So the PMTs are quite happy. I think. We have lost some of them. The ones that we have lost, most of them were lost during deployments. And so what happens there is, I'm not sure if I have a picture, but what happens there is that when you deploy them, let's see if I have a picture. No, I don't have a picture. But when you deploy them, the ice refreezes. And when the ice refreezes around the dome or the PMT, what it can do is it can pull it out of its cable and disconnect it. So the ones we have lost, maybe we can see it here, but the ones we have lost, essentially each of these PMTs is in a hole that we make for them. And when the hole refreezes, you can disconnect them, like this cable you see here. Those are most of them ones we have lost, but after that, it's been quite stable. But if they break, there is no way for us to replace them.
Okay. Thank you.
Yeah, thank you.
Any more questions from students? Yu-Hao, do you want to ask?
Yeah, near the start of the talk, you showed an image of the sun from Kamiokanda, and so I noticed the shadow. Yeah, this one. It's not circular. At the core, it's circular, but the outside shadow, it's not circular. Why is that?
That's a really good question. I unfortunately do not think I can answer that question. I don't really know exactly details of how they make it exactly this figure. So I would need to get back to you on that one. I don't know if somebody from Super Kamiokande remembers this, but if not, I will get back to you on that one. Sorry.
Thank you.
Ben Monreal says he doesn't know either. Okay, let's see. Corbin, do you want to ask?
Yeah, if you could hear me.
Yeah.
My question is, I mean, obviously the astrophysical neutrino source question and what those sources really are and where the neutrinos are being made is very interesting to a lot of people. But as you go higher in energy, eventually you'll expect that the cosmogenic contribution to the neutrino flux will come in, and presumably you know a bit more about what to expect those neutrinos will look like. I'm sure that at IceCube as it currently exists isn't quite able to say anything about that, but will these upgrades address that? And does this have anything to do, can you make a use of this in the context of your constraints on standard model stuff?
Yeah, that's a very interesting question. And so the cosmogenic neutrinos, let me see if I find a picture that shows the cosmogenic neutrinos. Okay, the question is, to rephrase it, is that there is another source of neutrinos that is expected from cosmic rays interacting with the CMB. That source of neutrinos tends to produce high energy neutrinos close to an EV, and it's very, very small flux. As far as we know, those neutrinos we have not seen so far. And we think that the IceCube Gen 2 array should have a shot at that. And the IceCube Gen 2 array is actually a combination of detectors. Actually, maybe I go back to that figure there. Let's see. What you cannot see here, or it's hard to say, is that the IceCube array is going to be a combination of 3 types of detector, the IceCube Gen 2. It's going to be an in-ice array, which is what you see below. That's approximately going to give you 10 times more volume. But then on top of it, there is going to be an cosmic ray array, which we call an isotope extension. And there is going to be a radio array connected to it. And so radio detection of high neutrinos allows you to have an even larger volume to see those. So the hope is that we will be able to get to those cosmic neutrinos. If we will be able to get them or not is tricky. If the cosmic ray flux at very high energies is mostly proton, I think we have a good chance. If it's heavy elements, it's difficult, but that's one of the science goals for sure. And then if we see those neutrinos, that's really interesting. What kind of physics you can do with that? Yeah, I will have to think about it, but I'm sure we'll think about something. But yeah.
Good. I guess Corbin asked a question. I can ask the question now.
Yeah.
Carlos, just a comment about new physics. You presented the way to put constraints on neutrino dark matter interactions, and also, yeah, for example, Lorentz violation, right?
Yes.
Take for example neutrino dark matter interaction mediated by a gauge boson, right? As you know, SO2 symmetry forces you to have the same type of interaction to electrons. Therefore, and the same for Lorentz violation. Of course, you can study that, but the fact that the charged electrons give you very strong constraints, it's hard to hide new physics in that particular type of interactions because, it's just SO2 symmetry that will hit you so hard that it's hard to really move forward. I don't want to say that the people should not do that, but it's really hard to hide new physics in the neutrino sector where SO2 tell you that you will modify charged electrons, and then you really hard to imagine you will get something from there, okay? And then the other comment is regarding just pure standard model physics. The nice thing about IceCube is that, can you show the plot where you have the cross-section with energy? Then IceCube is the only experiment that can measure can give you a value of the neutrino cross-section above, let's say, a few TeV, right? You guys go all the way to, can you show that plot?
Yeah, I have it. Just give me a second.
But I guess you agree with me about the first comment. It's really hard to hide.
It's very tricky. I mean, you need to do some model building. I
much gymnastic that it's hard to do that.
I agree 100% that you have to do some gymnastics there for sure. I agree with that. It's not like it just comes. The naive things you will write have problems, so you need to put some things.
You really need to okay.
And then the other comment you had, which was the one about the cross section.
Right. That would be nice. Because you could get theta W a very high energy. I am curious. I remember one of your collaborators wrote papers about that, I believe. And the question is, how good is the precision because once you go, anything that has to do with LHC or any previous experiment, you can go and try to see if the standard model is doing a good job all the way to high energy up to what IceCube saw. But I guess the errors are pretty big, right?
Yeah, our errors on most things are quite large. Let me show you the plot you want, which I think is this one here. So this is the cross-section measurements. I'm not sure if that's what you meant. So the cross-section measurements like these energies. So these are our measurements. And we have also measured the inelasticity of the neutrino interaction. This is here. So this is shown as a function of the neutrino energy. So this is let's say for neutrinos and antineutrinos, what you expect, and this is the measurement. So this is the Y distribution measurements. And this is a plot that came from this paper by one of Bustamante's papers.
Right.
Shows you that the cross-section measurements of IceCube, these are actually their own calculations, and these are our own measurements of it. But essentially what we are measuring is this part here, which cannot access. So we only have events down to like maybe like 1 or 2, which is this error here, you can see gigantic. Events of the PEV. If I skip Gen 2, we hope to get into this regime here, for not only if I skip Gen 2, but with the radio range. So yeah, we will be pushing that, but the error bars are quite large still.
Thank you.
So just to clarify something here, the cross-section measurements, these measurements are done by looking at the Earth transparency. So essentially use the Earth at very high energies becomes opaque to neutrinos. And so you can measure that in this range. The inelasticity measurements we actually can do at lower energies, right? Because then we just measure the shower and the associated track, and we can do the ratios. But is that the plot you wanted to see?
Yeah, no, I remember this plot from Bustamante. I think that is the right one.
Yeah.
Is it possible that you could have neutrinos that are massless, exactly massless, and all the flavor oscillations are just caused by Lorentz Violation somehow?
So the answer is no, but that's something that people thought about. Mm-hmm. And the reason is that the Lorentz Violating operators do not produce the right energy dependence to oscillations.
Plus, SO2 symmetry, will modify the charge fermion sector. It's really hard to hide, just SO2 cross one invariance, right? It's very hard to hide Lorentz invariant physics in the neutrino. It's just too hard. Then you will modify neutrino, but you will modify charged leptons. And we know the leptons pretty well. The leptons behave pretty normal. So, how you can imagine to do that?
Well, I could imagine doing like in the Dirac equation, having some mixing between the time derivative terms and the gradient terms.
That is fine, but the SO2 is related neutrinos on charged electrons. Then you will modify the electron and the neutrino. Then we know how the electron behaves. Then of course you can do gymnastic, but the SO2, the standard, we have the standard model. The Dirac equation is just too naive.
Yeah. Okay.
My recollection was though that, so we did this collection of different, this is from one of these Kostelecki's tables of that, and we tried to look at all tests of Lorentz Violation. You can see them, also my slides being shared here. See? Can you see the slide?
Yes.
Yeah.
So you can see we did this study, and maybe we'll have to recheck the issue with the charged leptons, how well it's been measured charged leptons. You can see here the different Lorentz Violating operators organized by dimensions and where you get the best constraints. So for example, when you look at dimension T operators, you have these torsion pendulums, mu and G minus 2 experiments as support. And then you can see the constraints that we get from neutrinos and other things. So it really does depend. Like what I remember is like these higher dimension cases, the charged leptons were not so strong.
Yeah, the taus. You have some freedom in the tau, but
so I think it does depend a little bit on how you do it. I will have to recheck this table to see where the charged lepton constraints are, in these sort of operators here.
It's not impossible, but it's close to that.
Will you be able to cross-check the Anita events? I mean, let's see Anita-like events with the upgrades.
That's a really good question. The answer is yes. And we have done an analysis looking for the Anita events. So what you do there is you look for time constant signature to the Anita observations, because we know at which direction does the Anita event come from and at what time. And so what we do is in that particular direction and time, we see if there are neutrinos. And the answer is we don't see any neutrinos at that same time in the same direction. And so because of that, we actually can rule out that the Anita events are neutrino related or neutrinos. They could be something else, I guess, but they are not neutrinos.
Okay, can you repeat the statement about the dark matter distribution and when you were talking about the dark matter distribution, the number of events from IceCube? Can you show this again? You say, is the distribution following the dark matter profile density? What is the statement that you made there?
This one here.
No, after that, I think that one, which is the,
So here, what I was saying is that there is the galactic dark matter distribution shown here as color scheme. And so I think this is the inasto profile, but I don't remember exactly. And so the idea was here that if you have an interaction, you can have essentially absorption in the neutrinos and dark matter. And then you have a disappearance of neutrino events through the galactic center because they're going through a higher density of that or larger dark matter column density. So then the neutrinos will sort of like anti-trace the dark matter column density. Does that answer your question? Is that what you were asking?
doesn't look so easy, yeah.
It looks, yeah, it's tricky. And I think that it's one of the cases where you see this distribution has like not so many events, right? There are gaps.
If you just think about a toy model, dark matter neutrino, let's say a contact interaction, you will need maybe, you know, you have to worry about the annihilation dark matter to neutrinos bounds. I don't know how large you can, suppose that you want to just to see what kind of interaction you can put to match both things, but it doesn't look like you have the precision to know about
that. So here the neutrinos disappear. It's not that dark matter decays into neutrinos. That's another thing, which we have also looked into. But that's, so essentially we have two types of searches. One search, we look for an excess of neutrinos from the electric center. And in the other search, we look for a deficit of neutrinos from the electric center. And so it depends if the dark matter is decaying to neutrinos or more particles. And in the other case, it's this sort of secret interactions. But in that second case, the dark matter is very light. It's like MeVs.
Okay, so if there's no other questions, we'll conclude the main part of our colloquium.